Ready? Okay. Welcome, everyone. Can we all give a warm welcome to Rick Branson from Instagram, who will be giving us a talk on messaging at scale with Instagram.
Hey guys, thanks for coming. This is an awesome crowd. Great to be here at PyCon. But we'll get into this quick. They told me I had 30 minutes and I have like 2 hours worth of stuff, so I had to cut it down a lot. So really, I'm going to talk mostly about the meat of this, which I think is most applicable to everybody here, which is kind of how we do async tasks at Instagram. We're a big, Python Django shop, and we have needs to throw things in the background and not do them in the web request. It kind of starts here with our feed. And for those who aren't familiar with the product, basically it's a photo sharing app. It's social, so you follow people, and you see this feed when you open the app, which is basically all of the people that you follow, all of the photos that they're posting. It's kind of the core of the product. Photos are time ordered, so the newest photos appear at the top. And kind of when when you kind of approach how to render this sort of feed, kind of a naive approach is sort of the most basic SQL ignorant kind of way to do it. Doesn't scale very well, but this is kind of, if you could sum it up, what we're doing here. The problem with this is that it just goes on forever. Fetch all the accounts you follow, then take all the photos from those accounts, all of them that have ever been posted, sort them by creation time, and return the first 10. You probably are throwing away thousands and thousands of photos at that point. Not a super great way to do it. So what do? We basically keep a list of media IDs for each user. We store this in Redis, and it's really simple. It's just an ordered list. Has a list of media IDs in it, and it's queried by the user ID. So we just do a simple lookup to get that data. But we have to figure out how to kind of populate this when a user posts a new photo. So say we have this media ID 943058139. We have to go get all of the followers that user follows and insert it into each one of their feeds. This is called a fan-out-on-write approach. It basically has an O of 1. It's a fixed time cost for reading, but it also has a much larger cost for writing. But that's fine for us because we read a lot more than we write, which is what makes it work right. This, of course, has reliability problems, though. The previous approach is just insert one thing into the database and kind of figure out everything, pull everything together at read time, which is not super great, but again, we have to address some of these problems. Reliability problems with the fan-out-on-write approach, database servers fail, the web request is a scary place, you kind of want to get in and out as quick as you can. And then there's the Justin Bieber problem. He has like millions of followers, and you can't realistically deliver to any more than a few thousand within the 100 to 500 milliseconds you have in the web request cycle. So we use sort of an async background task system. It looks like this. It's pretty run-of-the-mill. Many of you are familiar with systems like this. We insert a task into a broker, and then we have workers that listen to tasks on that broker and work on them. The benefit of this is that if one of these workers fails or crashes or dies or whatever, data center fires, whatever, basically it'll go back to the broker, gets redistributed to a new worker, and that kind of gives us the reliability we need. The other thing that we wanted to do with this is we do this thing called chain tasks, where we don't want to do all of the deliveries all at once. We don't want to take all of Justin Bieber's followers and deliver them in one huge chunk. So what we do is we break it into pieces. So we have a bunch of small tasks that get executed, and it works kind of like kind of a recursive function in a way, because we basically call this starting. We started out with calling this task. We give it a kind of a beginning cursor of nothing, and then it recursively calls tasks with a new cursor until it finishes, basically. So it walks this list of followers until the very end. Benefit of this, we get really fine-grained load balancing. It means that one worker is never working on a task for more than a few seconds. We can deliver to 10,000 followers per task in about a second and a half. And then, of course, it means that when you fail, or you have to reload your code, or you have to, any sort of problem that would happen there, it's a very low penalty. You can kind of resume the work where you're at. It's kind of a really elegant way to do that. So what else do we use other than the feed? What else do we use this async task system for? We do things like we cross-post to Twitter and Facebook and Tumblr. We have a search indexing system that's offline. We do spam analysis, permanent account deletion, permanent data deletion. We also have an API hook so you can get callbacks when photos are posted. The genesis of this in the beginning was a system called Gearman in Python. Gearman is a really simple, it's a purpose-built task queue, originally written in Perl, now it's written in C. It had really weak framework support when we were using it. We basically had to build these like ad hoc worker scripts that would get kicked off in the background, and we had these like messy cron jobs that would restart them and things like that. It was no fun. It was a mess to add new job types, et cetera. I mean, this isn't necessarily Gearman's fault. It's like we needed a framework and we didn't have it and we didn't have the time to build it. It was also really rough in production. You really can't use the persistence. It's just really, really slow. It's based on MySQL. So we basically ran it in memory. If it crashed or ran out of memory or the box died, that was it. We lost all those tasks. Not very good when you can't kind of get back to where you were. It's polling based, so the workers actually poll Gearman. It just didn't scale very well. It was single core, et cetera, et cetera. We probably should have just used Redis, honestly, at this point. So we needed a fresh start. Excuse me. And of course, the overall warning is, we basically had to build this in a finite period of time, so we're probably doing something stupid. Nothing is ever perfect. But we hope that this knowledge is useful for you guys still. Celery, so enter Celery. Celery is a distributed task framework. It's a highly extensible, pluggable, feature-rich, mature. It's got awesome tooling. It's this really awesome. If you've never seen it, it's actually probably one of the best Python open source projects out there. It's got awesome Django support. It's got this thing called CeleriD that makes running things and keeping it, if things crash, it restarts them and things like that, which is awesome. But the first question you have when you start using Celery is kind of which broker you're going to use to kind of buffer your tasks and distribute them out to your workers. So we looked at kind of what we had and what was out there, and we kind of came up with 3 candidates. First one is Redis. We already used it. We had experience with it. It was very fast and efficient. But unfortunately, it's polling based. It does have a pub subsystem, but it still depends on sort of polling after the fact, especially with a busy worker to do it. The replication is kind of bring your own tooling, which is arguably good for a system designed to do a lot of different things. But for us, we were looking for something a little bit more batteries included when it came to replication. And of course, Redis is an in-memory system, so ultimately, if you end up running out of memory, you start losing data, which is no good. We also looked at Beanstalk, which is a purpose-built task queue. It's really cool. It uses kind of a similar variant to the Memcache protocol. It's written in C. It's very fast and efficient. It pushes to consumers, so it's kind of hitting some of these right buttons. It spills to disk, but completely no replication support at all. Even we tried, dreaming up these horrific, Rube Goldberg machine replication ideas, and that was just not going to work. It's also not really useful for anything else. It's great that something is purpose-built, but you also try to find other ways, once you have experience with the tool, to use it in other ways, and Beanstalk just didn't work out for us that way. So we ended up in RabbitMQ. RabbitMQ is kind of where, if you read all the Celery documentation, they'll push you towards. It's reasonably fast. It's nowhere near as fast as Redis and Beanstalk, but that's fine. It meets our requirements. Spills to disk. The replication setup is like the easiest thing in the entire world to set up. You literally just point the nodes at each other, and they negotiate and decide who's the master, and they'll do their own master election process and all that stuff. So it's really batteries included there. It's got great Celery compatibility. It's useful for other use cases other than just async jobs. There's a bunch of messaging use cases that I wanted to talk about, but I can't. Only downside is we didn't know Erlang. Not a lot of people do. That's fine. The code's really clean. You can start reading through it. It makes sense, so it was fine for us. Our setup, we use RabbitMQ 3. We were using 2. 3 is a lot faster. We have clusters of 2 broker nodes that are mirrored, so they straddle availability zones, and I'll kind of show you what that looks like. We scale out, so we add more capacity of throughput by adding more broker clusters. We run an EC2. The instance size we use is C1x large. We RAID the instance storage, so we don't depend on sort of the EBS, which is the SAN storage of EC2. And we are way over provisioned. The reason for that is that if we have issues or like we have big spikes, we can kind of handle big changes in our load pattern. We can burst up to a lot of extra capacity. Great. Alerting, we use this thing called Sensu, which is unfortunately written in Ruby. We basically just monitor an alert on the queue length. We also have monitors on like failure rates and things like that. We use RabbitMQ CTL list queues, which is just this command line tool. And we feed that into Sensu, and it basically picks those up and feeds them into the monitoring system. For graphing, we use Graphite and StatsD. We basically have used these Celery hooks to feed any of these status messages into Graphite, so we can kind of graph how tasks are working, when they're failing, when they're having to retry, et cetera. Great for monitoring. Our topology kind of looks like this. So we have a bunch of workers, we have a bunch of web boxes, and we kind of feed them. We use basically a round robin approach to select a broker, and we just sort of evenly distribute them across the set there. Our publish times are, and these are, again, this is a very conservatively built system. We're pretty happy with the performance that we have. It's not like blazingly fast, but again, this is synchronous replication. It has to go to multiple availability zones, et cetera, et cetera. Gearman, again, we were doing 60 milliseconds, so this was a huge improvement on that. We push about 4,000 tasks per second through the system overall, kind of sustained. Again, we're way over provisioned. This is our CPU at like 20% across our 3 clusters. So you're like 4,000 tasks per second. That's not a very big number. We are doing a lot in these tasks. I will remind you that we have 25,000 app threads or processes, like Unicorn processes, pushing data to these brokers. They handle over 10,000 connections. No problem with doing rolling restarts and like pounding these things. It works awesome. We span data centers. The most important thing about, I think, this setup is that it's designed for scale out. So, there isn't sort of this like, oh, we hit a wall at some point. We're pretty confident that we can scale this out pretty far into the future. One of the biggest sort of motivations for switching to Celery was, dramatic pause, that basically we could bring new engineers up and running really quickly. That was one of the most important things. And I'll show you kind of what it looks like. We can deploy new job types without a lot of work. And we have to do a little bit of config hacking to make this work for us. This is basically what a Celery job looks like. It's really easy. You technically don't even need the routing key on there. We run tasks on their own queues, and we kind of group them so that when they start backing up, our alerting, we're not getting like, tasks are backed up. Now go find out which task is backed up. We know which ones are backing up, and we can take immediate action. To call a task that we created, we just call the function with .delay and pass it the arguments that we want. It's really, really simple. It's really great. We talked a little bit about scaling out. How does that work? Unfortunately, when we started with Celery, it only supported 1 broker. So we created this little hack shim thing we called Kombu Multi-Broker, which is Kombu is the library that Celery uses to talk to all of the brokers. It's a shim. It's on GitHub in my account. And basically the idea is to use the multiple brokers in a round robin fashion. The downside of this is it breaks a lot of the Celery management tools. Unfortunately, you may or may not have to do this depending on your workload. We're hoping that this changes in the future, but at this point, we're kind of in the, not using some of that tooling. Concurrency models, Celery supports kind of the default, which is multiprocessing. It's just sort of your typical pre-fork model. It also supports Eventlet. We don't use that. It supports gEvent. We do use that. And threads, they literally say it's a minefield on the docs, so I wouldn't probably use that. So let's talk about gEvent. gEvent's awesome. You can get a lot of concurrency, but the real world, not everything works on gEvent. So we have to run some tasks in gEvent mode, some tasks in multiprocessing mode. Thankfully, there's this thing called CeleryD Multi, which basically controls you can have like a whole bunch of workers running on a single box. It'll handle starting and stopping them and making sure they're running and doing status checks and yada yada. We hack the config, so we basically have this, we have this basically set up where we have our qconfig, and then we group them into these task groups. Again, one's for evented tasks, one's for normal tasks. There's a little bit of hack on the standard Celery setup. We set the Celery queue group option sort of at runtime depending on which worker mode we're in. gEvent, we use it for anything network bound. Facebook API, Tumblr API, background S3 tasks. When we want to go get a URL for spam, anything that's sort of, we're spending a lot of time on the network and not a lot of time on processing. Of course, that brings us to sometimes we actually have to do something that is both network bound and, at first, and then maybe we need to take some action. So that kind of looks like this. We actually split the job into 2 pieces. It seems really simple, but this works really well for us. Basically, we run the thing that's rare, relatively rare. For instance, if we're doing a spam check, most of those URLs come back clean. If we do need to take an action, like deactivate a user account, we do that in a sort of the multi-process mode, which all of our databases work, Redis works, everything works in that multi-process mode. We don't have to worry about it. So that works great. Another problem we ran into when we deployed the system is that slow tasks monopolize workers. And that basically means that you have a batch of tasks that you're running, and they tend to, the last long tail of those tend to basically run on the workers, and they tend to monopolize the amount of time. So what we do is this is kind of what it looks like. The main process in Celery will go fetch a bunch of batches, and then distribute them amongst the workers until it sort of reaches the very end. And of course, the last 2 tasks, the slowest ones, will always be at the very end of that batch. And then it goes and gets another batch. So this is a problem. We considered several options. One of them was run higher concurrency. It's obviously really inefficient. You get kind of run against other problems, other walls, you run out of memory, et cetera. You can lower the batch size, but again, that's also really inefficient. Doesn't really change very much in the way of that. And then I think the thing that we ran up against that really kind of worked for us was kind of a pattern that's used in a lot of concurrent systems, was to separate kind of your slow and fast tasks into different workers. So we kind of leverage the same sort of config separation of tasks, and we have a fast worker, and we have a default where everything stops. We also isolated our feed delivery. We found that anything that's sort of critical that you never want to get backed up, you kind of need to run your own sort of worker, a separate set of processes for that. Just to be clear, these all run on the same machine, and that CeleriD multiprocess will, basically create a whole bunch of CeleriDs that run each type of this, each task group. Concurrency levels, this is specifically for the ones that we run in multiprocess mode. We run 14 child processes for the fast queue. We run 12 for the feed queue, and we run 6 for the default. This runs on 30 EC2 instances that are C1X larges. Most stuff starts in default and gets promoted to fast as it sort of gets proven out. I find that to be a really useful pattern. We run I think our G-Event stuff runs 48, a concurrency of 48, and that seems to work fairly well as well. Other problem, tasks fail sometimes, big surprise. How do we deal with this? Celery has a really great retry facility. It's parameterizable, so basically this is almost literally the code that's in our code base. Sometimes we have to deactivate media for whatever reason, and basically we do that in this task, and sometimes we get these remote operation errors, which are retryable, and so it's kind of a strange thing to raise this function the function that has called, but I don't know why it's this way, but it is. So that works really well. And the cool part about this is you can say countdown 60 seconds. There's a bunch of other parameters. I'm just literally touching on the very tip of what Celery can do. And the nice part about waiting is that obviously if it's a temporary issue, like S3 is backed up or there's some backend system that's dying, you give it some time to breathe, and then you can kind of, everything will resubmit. And Celery handles this whole process for you. Another problem is that worker crashes still lose tasks. And this seems strange. How does that work? Well, the normal flow is that in Celery, we get our tasks, the worker starts the task, and then we send an acknowledgement to the broker, and the broker forgets about it at that point. And ACT says basically, I'm done with this task, I never want to see it again, goodbye. And then after that, the worker finishes the task. So between 3 and 4, there's basically a chance for to basically lose that task if the broker crashes, if the worker crashes, if the box dies, et cetera. So what do? Celery supports this thing called ACT late, which basically just switches these two. It does get tasks, starts the task, finishes, doesn't send the ACT until it actually finishes. It's really easy. This is, again, cut and pasted from our code base. We just add this ACT late option to the decorator. So it's really easy to configure. And I know a lot of you are asking, why not just do this all the time? It's the most obvious question. I ask this question we had to dig into all this. Basically, your tasks have to be idempotent if you want to do this everywhere. Idempotent just being that if you keep running the same task over and over again, it will have the same, effectively end up with the same result. Some tasks, just that's not what you want to do. For instance, we have to do a lot of work on our feed delivery to support duplicate items in the feed so that those get collapsed. We don't want to show the same photo multiple times. Again, like a lot of things, this probably is the case. You probably have to make your tasks idempotent anyway. You should probably try to do that. This mirroring system that we use in Celery can cause redeliveries of tasks, cause them to get ran twice. There's also this thing called FLP impossibility, which is this paper that was written that kind of proves that you have to deal with this anyway. And I'll rant about that for a second. There's no such thing as running tasks exactly once anyway. You kind of have two choices. And the reason for this is that it's impossible to tell whether a system that you've sent something to is either dead or extremely, extremely slow. This theory proves it. There's a bunch of math behind it that I don't understand. So I'm going to trust the mathematicians. Basically, our choice boils down to this. Do we retry when we detect any kind of failure, like a timeout, or we don't retry? If we retry, we have the chance of having duplicates, duplicate tasks. If we don't retry, we don't know if the task actually got ran or not. So you have to choose between those two because of this stupid theory, or proof, rather. Damn you, physics. The other thing is, early on, we noticed like overloaded brokers were dropping tasks, which sucks, as you might imagine. We didn't understand why. And the reason why is because you really need to turn on this publisher confirms mode. By default, AMQP, which is the protocol that Rabbit uses to talk to the clients and the publishers and the consumers, doesn't actually give you an acknowledgement when you send it a task. You actually have to ask for that. There's various reasons for that. This kind of hurts performance a little bit. I think something like 25 to 50%, depending on what you're doing. Basically, this tells a broker to send me back a acknowledgement. We basically had to kind of use our shim that we wrote for the multi-broker stuff to force it on. I've been trying to figure out how to get Celery to do it. Maybe somebody will chime up on how to do that with Celery. FLP happens again here because there's this very rare chance that the confirm gets cut off before it gets to you and the broker still queues the task. If you retry it, you still can get duplicate runs. Damn you, science. Other rules of thumb, so we've talked about a bunch of stuff. Here's kind of like a few odds and ends. We generally try to avoid using these async tasks as a backup mechanism. So in case something starts failing, we queue a bunch of stuff in the worker, in these workers. That kind of option backups generally just don't work when you use them unless you're using them all the time or testing them. You usually end up doing things like you don't have enough capacity on the Rabbit, so then they die, which is just exacerbates the problem. So you either run it. I feel like we have kind of two ways we do it. We either run it through the queue every time, or we just try. Basically that's our option. The other thing is we try to only pass these sort of self-contained non-opaque data through as arguments. We don't try to construct fancy stateful objects and send them through. It uses Pickle to serialize them, which Pickle works really well, except when you reload code and there's different versions and yada yada. So we try to stick with things like strings, numbers, and then arrays, lists, and dicts of strings and numbers and arrays and lists and dicts as arguments. That seems to work fairly well for us. The other sort of point, tasks should usually execute within a few seconds. We just found that it's kind of an anti-pattern, just that if they last any longer, it takes forever to restart the brokers if there's a whole bunch of tasks that take a long time when you're trying to do kind of continuous deployment. We've just found that it just doesn't, there's a whole laundry list of reasons why this is bad. So we use this soft time limit of 20 seconds. We'll basically throw an exception. When you hit that limit, it'll log a message. We also have a hard time limit at 30, which will just basically kill the process if it takes that long. Again, when that happens, if you're using these different fault tolerance options like the acts late, it'll actually get re-enqueued, which is great. So the future, we'd really like to get better at RabbitMQ performance. Again, we're definitely not experts in RabbitMQ performance. We just kind of threw boxes out there, and it sort of seems to work fairly well. we like to get better at this rather than just sort of, waving our hands in the air. We don't use a lot of the features, honestly. I feel like we use like 25% of the features of Celery. One of the features is result storage, where you can actually store the results of those tasks. That's a little more useful for people that are doing more sort of distributed computation with it. Things like, we'd really like to see like errors, exceptions, and things that come back from tasks and be able to kind of track those down and say, oh yeah, this exact task ran at this time, and these were the things that ran. We also would like to have a single cluster for control queues. I talked earlier about how we're breaking all the management tooling for Celery. What would fix that is if basically we could say, use a different cluster, use a dedicated cluster for those control queues. So Celery uses queues to actually communicate with all the workers when you're using the management tooling, which can do things like scale the size of the pool and do rate limiting and do all this on-the-fly stuff we'd really like to be able to leverage. And then eliminate the shim. Celery now supports multiple brokers. And it's just a matter of eliminating that shim as far as just making it work, as well as figuring out the whole publisher confirms scenario. So thank you guys. Any questions?
So we basically have the same setup. Like we have a cluster across multiple EC2 zones.
Yeah.
And one thing I've been curious about is like, how do you handle when a zone or multiple zones go down? Like, how are you sure like messages are still going to the queues? Because like right now we kind of have like a load balancer, but it's only in one zone. And obviously it seems like maybe you go across multiple zones. But
Yeah.
I'm just interested in how you guys handle that.
So one of the things that the multi-broker, so Celery uses, or RabbitMQ uses synchronous replication. So when you actually get that confirmation, it's been replicated on both brokers, and it'll detect network failure and do the failover by itself. On the client side, we basically just populate them with the host names of all of the brokers that we have, and they'll actually detect failure, blacklist hosts. This is part of the Kombu multi-broker stuff. They'll detect failures on hosts and then rotate to different hosts when we have failures. And it's worked tremendously well.
What do you do to handle updating the tasks in a relatively seamless fashion?
There's a lot of facets to that. There's things like if the arguments change and things like that. We've had to do this a few times. Generally when we add arguments to a task, we'll either sort of create a proxy that will just generate, create V2 of the task and then just create a proxy that'll call it so that, because we do rolling restarts. The web layer as well as the Django layer, the worker layer will actually, we do rolling restarts of those. So like we could have both code versions out at the same time. The other thing is we tend to use Quargs for like if we need to add something on the end. So those tend to be compatible. We're still kind of working that out, honestly. We haven't really ran into it a lot, but we have ran into it a few times before.
Hey, I kind of worked on a similar thing with messaging queue.
I'm sorry, I can't hear you. There's a lot of noise.
Okay, I worked on messaging queues in one of the projects that I worked on. One of the things that I noticed was with the workers, you said that you can switch from one queue, from a fast queue to a slow queue, or from like how does that switching happen?
We basically just change the configuration and do a rollout.
Oh, it's not dynamic.
No.
Oh, okay.
We do our rollout process is really designed to have fast turnaround. I mean, we could make it dynamic, just a matter of making the config update and I think also Celery will basically, I don't know if it actually supports that kind of dynamism or not. It supports a lot of stuff, so it wouldn't surprise me if it did.
I was not clear about that, so I kind of assumed that it was a dynamic switching.
Yeah. It's not for us, and it's only just because we deploy continuously, so it's not really a problem for us to make a quick config change.
So sorry, unfortunately we started the talk a bit late, so I'm going to have to cut it short there. Can we all give the speaker a very thank you very much?